Okay, we're going to start with to learn about the structure of the radicals, so you know what's it look like, and so you know what to do with it. Carbocation, you've seen before many times now. This carbon and sp2 carbon, right? Which means it's like got a p orbital left, which is empty, nothing there. The structure in it's the trigonal planar, is flat, right? And all right, now let's say, imagine though, if I add a lone pair, if I were to add lone pair on this orbital, okay, lone pairs right here, what's going to happen to the geometry of this carbon? We will stay as trigonal planar. No, it's not. The lone pair will push these two groups downward, push it down, push it down, push it down. That's the electron repulsion. You're going to get something that look like trigonal pyramidal. Right, so this guy get pushed down. Right, so the lone basically I'm just talking about like when the nucleophile attack, the nucleophile put everything else down. Lone pair do the same thing there. Right, so carbon ion and sp3 carbon now. Right, so there's no p orbital left. All right, so trigonal pyramidal, the geometry. The structure of the radical is somewhere between this. This is flat. This is trigonal pyramidal. The structure of the radical is they call it a shallow pyramidal. Right, so it's an sp2 carbon kind of sp3. I mean, it can look either way. They can go back and forth between the two. Right, the geometry is shallow pyramidal. This is not a lone pair, just one electron. So the degree of pushing electron repulsion is not as much as from the lone pair. Push everything down. This guy just one electron. Right, so it's not neither it's neither trigonal planar, neither trigonal pyramidal, but it's somewhere between. So we call shallow pyramidal. Okay, and also they just don't say this pyramid can invert up and down. Could be up, could be point down. Right, this will play a big role in terms of predicting the stereochemistry of the product. You will see it later. Okay, and all right. Drawing the resonance structure just like the lone pair. If you still remember from like chapter 1 or chapter 2, the lone pair next to the double bond is localized, right? Because this is sp3 carbon, but the sp3 orbital right here can line up parallel with the p orbital of the pi bonds, right? And allows you to draw resonance structures. You can draw the curved arrow like that. The radical, also in an sp3 carbon, sp3 orbital, can rotate around. Maybe it's not as trigonal plane or tetrahedral, just like this carbon, but it can rotate around and parallel with the pi bond, with the p orbital of the pi bonds. So you can draw a resonance structure as well. But the arrow that you're going to draw is different, not a double-headed arrow. You have to use a fish-hooked arrow. Okay, so I'm going to show you right here. So the double bond going to form here. You need 2 electrons, so one here. The other one is one of the 2 electrons from the pi bond. Look like that. All right. Now, the pi bond, which is 2 electrons, used to be here. One's go from pi bond with this. The other one have to stay on this carbon. We break the pi bond back actually. All right. So you're gonna have the radical on the left side and the double bond on the right side. You can draw like this as well, right? Wash out the arrow. This is a fish hook arrow, not a double-headed arrow like we used to. Okay. For the localized lone pair, just like a lone pair, the lone pair on an sp2 carbon, which already participate in the p orbital, the pi bond here, localized. They can't pair up. They can't be parallel with this 2p orbital. Same thing with the radical. The radical which on an sp2 carbon, this orbital, no ways on Earth this guy can parallel with these 2p orbitals. Okay, so that's localized. You cannot draw the resonance structures. All right, that's a little bit about the structure and the resonance of radical. Let's talk about the stability.